All right, welcome back, the genius. So in this session, let's talk about bitwise shift operations. Okay, we have talked about the AND, the OR, the XOR, and the NOT operators. But let's take a look at the bitwise shift operators, how they work and how we use them. What? A bitwise shift operation moves the base of a number left or right by a specific number of positions. You remember that the base we are talking about is a sequence of base, all right? So a bitwise shift operator or operation will move the base, either moving them to the left or moving them to the right, okay? So now the bits shifted in or out depend on the operation, whether it is logical or arithmetic. Don't worry, we're going to explain more what we mean by the operation being logical or arithmetic. Okay, so now let's take a look at the left shift operation. Okay, I'm going to take my time to explain these things. I'm going to take my time to explain this. So now, this left shift operator, it shifts all the bits to the left, all right, and it will fill zeros on the right. So it will shift all the bits to the left, then it will fill all the zeros to the right. So before I continue, it's equivalent to multiplying the number by 2 raised to power n. Sorry, this is 2 raised to power n. Now, the n means the number of bits, okay, number of bits. So now, look at the things you need to get here, right? When you do a left shift operation, it will shift all the bits to the left, all right? Then it will fill the remaining part to the right. So let me show you using an example. Let's say I want to do the binary representation of 8 is I believe is 0, 0, 0, 1, 1, 0. Am I correct? No, this is 6. This is 6. 1, 1, 1 is 7. Okay, so I believe um is 1, 0. Okay, it is I should be 1, 0, 1, 0, 1. 1, 1. No, I believe this is okay because yes, this is okay, this is 2 raised to power 3, which is 8. No, okay, this is more. This is 8, 4, 2, 0. So this is more than 8. Okay, so this is not 8. I want to get 8. 0. Okay, so I will delete this. 4, 2. We need to have 4, 2, 2. Okay. I'm sorry, just don't mind what I'm doing. I want to have 4, 2. Okay. We can have 1, 0. Okay, yeah, I think so. All right. All right. Don't bother. If you don't understand what I'm doing here, I don't expect you to understand it anyway. Okay, but it's a trick I'm using to get it. So it is 1, 0. Yeah, 0, 0. Because remember, this is 2 raised to power 0. All right, this would be 0 minus times 2 raised to power 0, 0 times 2, and this would be 2 raised to power, following the positional, the positions, the positional value. So this would be 2 raised to power 1. This would be 2 raised to power 2. All right. Sorry, then this would be 2 raised to power 3. Now, it doesn't matter because anything that is multiplied by 0 will give us 0. So all these things will be what? 0. Then this one will be 2 raised to power 3, which is 8. So this will be 8 plus all the zeros will be. So this is correct. Okay, don't worry. If you want to learn this my trick, go to the WhatsApp group and drop it. Go to the WhatsApp group and drop a post that you want me to teach you this trick, the way I was able to get this value. Okay, so now if I want to make a shift, I want to shift this to the left. I want to make a shift I want to use the shift operator. I want to do to the left and by 1 position. All right. So if I'm to perform this thing, now what it means is this. Remember, the left shift operator pushes all the base to the left. So what we are doing here is this. We are moving towards this direction. All right. We are shifting it towards this direction, towards the left. So it means that it would, when it pushes it to the left, all right, it will add another, it will push it to the left. Basically, okay, let me give you the quickest trick. If you want to push to the left by 1, all right, just take this 0 here, this whatever the number is here, all right, take this one out. Take this one out, then add it here. Do you understand? Take this one out, add it here. So basically, we're now going to have 0, 1, 0, 0. So we are pushing the bit to the left. So we are pushing it towards this, and we are pushing just by one bit. So if we push it to the left, we'll take this one out, and then we would fill in this other side with 0. So let me go back to the slide. It says, all right, so let me go. It says it shifts all bits to the left and fills 0 on the right. Okay, it shifts all the bits to the left. Okay, and fills all zeros to the right. Fills all zeros. So it shifts it to the left, then fill it with zeros. All right. So we have shifted this to the left. Okay, and then we took this one out and put it here, basically. So we have shifting towards this way. So this is what we have here. So we are pushing everything this way. All right. So when we push it to this side, all right, we are now going, instead of having 3 zeros, then we'll have 2 and then have this one here. It's somehow tricky, but it's okay. And again, another point to remember is it says it is the equivalent to multiply the number by 2. Okay, so that means we did this. This is wrong. Okay. Um, okay. I think okay, I'm just coming. I'm coming. Now, this is to the right. And to the right. Okay. I'm sorry. What I did was pushing to the right. Okay. Yes, because my calculation is not correct. Okay, I'm sorry about that. Okay, so this is the reason why I was able to find out that I got it wrong. Because when you do something like this, remember it says it is equivalent to the number. Let's say this is 8, right? This is 8. So when you do shift, if you do left shift, it is equivalent to doing 8 multiplied by 2 raised to power n. And in this case, n is 1. You understand? N is 1. So this is equivalent to 2 raised to power 1, which is 8 times 2, which is 16. But if you see this, our result, we're only getting 4. So what I did here was shifting to the left. So pardon me, let's start afresh. All right? It's an honest mistake. Sorry about that. This can be confusing. So one thing you need to understand is that in case you find yourself being confused, when you do the operation, you cross-check it. So I did it and I cross-check it and I didn't get it right. So let's continue with 8. This is 8, 1, 0, 0, 0. And then this is 8. And I'm shifting by 1. I'm doing left shift, all right, by 1. So basically, all right, basically, it pushes everything to the left. So what will happen here is this. It would push this guy, all right? The last thing we did was we took this guy out. So basically what we are going to do here is we are going to, okay, so now let me do more of, let me do 8, instead of this, let me do 8 bits. Instead of just representing with 4, let me do 8 bits. Okay. All right. So now if I shift to the left, okay, I am actually taking this guy. I will take, because I'm doing only 1, I will take this guy out. All right. If I take this guy out, then they will now, if I take this guy out, what do we now have? We now have 0, 0, 0, then 1, 0, 0, 0. Then remember, it says it shift up bits to the left and fills 0 on the right. Okay, so look, this is what we have done. We have pushed all the bits. We have pushed it this way. All right. I just hope you get on my explanation. We have pushed this way and we have taken 1 out. All right. But then we need to fill in 0. We need to fill in the right part of it because now it still needs to be 16. So we need to fill it back here. So this zero has come here. This is the simplest trick because this is very, very tricky. So now if I want to do a left shift, this is how I do it. Since I'm pushing to the left, I will take the leftmost bit out. I'll take the leftmost bit out. All right. When I take the leftmost bit out, I will now fill in the remaining, the I will now fill in zeros on the right side of it. So if you check this thing now, what we have here is 16. We will get if you check this thing now, we have 16 here. All right, we have 16 here. So let me come. If we are to convert this thing to binary, this will give us 16. All right, because this will be 2 raised to power 4. All right. So, and every other thing will be multiplied by 0. So there's no need checking it. So this will just give us 16. So this is equivalent of 8 multiplied by 2 raised to power n. And in this case, n is 1. So n is 1. Okay. So I will now say 2 raised to power 1. And 2 raised to power 1 is 2. So 8 times 2 will give us 16. So that means we got it correct here. Okay. So it's very simple. All right. If you are doing left shift, okay, let me do it again. I know this might be confusing for some of you guys, but it's okay. All right. It's okay. Okay. So basically what I did here was, first of all, I'm pushing to the left. All right, because it's a left shift. I'll just by one bit. So since I'm pushing to the left, I'm going to cut off the leftmost bit. I'll cut off the leftmost bit and cancel it. All right. Then I will write out 0 here. This will be for this. This will be for this. This will be for this. This will be for this, and so on. So now I would now fill up the right side of it with 0. So since I removed only 1 bit here, I'll fill it here. All right. So what if I am to do 2 bits? What if I am to shift by 2? All right. If I'm to shift by 2, it's very simple. All right. I'm going to cancel 2 zeros here. It can be 1, it can be 1. It doesn't matter what the value here is. It can be 1. So since I have canceled 2 zeros here, what do I need to do? I will add 2 zeros here. Do you understand? I have canceled 2 zeros until all I have to do is to add 2 zeros here. So yes, I'll add 2 zeros here. This will no longer be here. Okay, let me do it. Let me start afresh and do it. It's somehow confusing, but try as much as possible to grab it. Just understand the trick. The trick is very simple. Okay, I have an 8-bit binary representation of 8. So 0, 0, 0. This is 4. Okay, sorry. This is 4. So I'm going to have 1, 0, 0, 0. So this is binary representation of 8. And I want to do left shift by 2. All right. So it's very simple. I'm pushing towards the left. All right. Since I'm pushing towards the left and I'm shifting by 2 bits, I'm going to cancel 1 bit, 2 bits. Do you understand? Once I do that, I will now bring this 0 here. 0, I'll bring this one here down. I'll bring 1. So this is for this is for this, and this will be for this. This will be for this, and this will be for this. But remember, since I have taken 2 zeros away from here, I'll have to fill in It must not be, it can even be, this can be 1. Do you understand? These bits can be 0 or 1. So once you take the leftmost bit, depending on the number of shift you want to do, or once you do that, as long as it's a left shift, once you remove, whether you remove 1 or you cancel 1 or you remove 0 here, you must fill it with zeros. You must fill it with zeros. So now I'm filling it with 2. I removed 2 here. I added 2 here. All right. So this is how simple it can be. And then it is, like I said, it is the equivalent of 2 raised to power 2 here, because now we are dealing with 2 bits now. This will be 2 raised to power 2. So it is equivalent of the number, which here in this case it is 8. 8 times 2 raised to power 2. This will give us 4. So this will be 8 times 4. 2 raised to power 2 will give us 4. So 8 times 4 will give us 32. All right, 8 times 4 will give us 32. And if you cross-check this value, you will see that we are going to have, this is position 0, position 1, position 2, position 3, position 4, position 5. So if I'm to do 2 raised to power 5 here, all right, every other thing here is 0. So no matter what I do here, 0 multiplied by anything I get here will still be 0. So 2 raised to power 5 will give us 32. So you can see that we got the answer correctly. All right. So whenever you do, you cross-check your answer. It is very tricky. I want you guys to be patient with these classes. And of course, while you're taking this class, if you don't understand it, reach out, post it in the WhatsApp group. Let us discuss it in a live class. Post whatever it's confusing you, and we'll discuss it in a live class, okay? All right. So this is for the shift. All right. This is for the shift. Okay. So now we also have the right shift. The right shift shifts the bits to the right instead of the left. It will push it towards the leftmost bit. All right, it will push it to the right. It will not push it to the left. And then for now, this right shift have, for the left shift, there is no complications. But for the right shift, when you're doing right shift, okay, for the unsigned integers, it fills with zeros. If it is unsigned, remember what unsigned integers are. But if it is signed integers, remember, okay, let me explain this thing with example. Let me explain with an example. So now we have done leftmost shifting to the left. So this time around, instead of doing 8 bits, let me do representation of 4. So I will do, okay, let's still do 8 bits. Okay, let's do 8 bits. Okay, so let me do 4 bits, okay, so that it will be simpler. All right, so I will say 0, 1, 0, 0. This is 4. This is actually 4, binary representation of 4. So if I do right shift, okay, if I shift by 1, all right, this is going to be the equivalent of 4 divided by, remember the shift was 4 divided by 2 raised to power n. And in this case, n is 1. Okay, so this will give us 2. When we do this shift, it should give us 2. But guess what? When you're doing the right shift, you should be careful whether you're working with unsigned and signed integers. Right now, let's assume this is unsigned integer. So we don't care about the most significant bit, because we are not using the most significant bit to represent the sign. This is for unsigned. This is for unsigned integers. Okay. All right. This is for unsigned integers. Now, if I do the shift, instead of shifting to the left, I'll be shifting to the right. Okay, so since I'm shifting to the right, I'm going to do what? I will cut off 1 bit because I'm shifting by 1. I will cut off the leftmost, the least significant bit, which is this one. I'm cutting off by 1. So what would I do? I will now take this one out, take this one out, take this one out. So which will now be, here will be 0, here will be 1, and here will be 0. But then I will need to fill in anything I took from here. I just took 1 bit, so I will need to fill in this other bit here. So I will now put another 0 here. If it is unsigned, all right, because now it is unsigned, we don't care about the sign. All right, there is no sign here, so we don't care about the sign. So if you watch now, this is giving us 2. This is equal to 2, so it is correct. So just like we did in the left side, we'll cut off the one part, then we'll fill in. So if I want to go by 2, all right, if I want to go by 2, if I want to go by 2 bits, that means I'm going to I will cut off 2 bits. I'll cut off these 2 bits, okay? Then I will only pick 1 and 0. Then, since I cut off 2, I will fill in another, oops, sorry. I will fill in. Okay, so don't worry. Let me erase everything and show you. Now, what we are doing here, we are doing unsigned integer and left and right shift. So I'm going with 40100, and I'm shifting to the right by 2 bits. I have shown the example of 1, so I'm shifting by 2 bits. So since I'm shifting by 2 bits, I'm going to cut out 2. I'm pushing towards this area. So since I'm pushing towards the area and I'm pushing by 2 bits, I would cut off this 2. All right. Then I will take this guy. I will take this 2 out like this. So here I will get 1. I will get 0. Then I'm going to fill in the space now because I took 2 bits out of here. I'm going to fill it with 2 zeros. Now this is for the unsigned. There is no complication. And so if you look at this thing now, this is still 4. So here we are doing 4. This will be 4 divided by 2 raised to power 2, because here now the number is now 2. 2 raised to power 2 will be 2. So 4 divided by 4 will give us what? Will give us 1. And that's what we got here. This is the binary representation of 1. So you see here, before you get to this level, you need to understand how to work with these binary numbers. The unsigned, the signed, you need to understand all these things. And please, in case you don't understand this thing, make a post in the WhatsApp group, in the foundational course, computer science foundational course group. Make a post and talk to us. Tell us what you're not understanding, so we can invite other people and you and other people to a live class and we'll explain and take your live questions. Okay. All right. So this is what we do. Now, this is for the signed. But now imagine that we are working with sorry, this is for the unsigned. Now, if you're working with the signed integer, remember, when you're working with signed integer, you have to be very careful with the leftmost bit, which is the most significant bit. So let's say we are still working with 4, 1000. All right. Now we are working with 4, and this is signed integer here. We are working with signed integer, not unsigned. Now you should be careful because remember the most significant bit, which is this one. All right. This is the most significant bit, MSB. This is used to represent the sign. And since this bit is 0, that means it is a positive number. So if you're working with signed integers and you're doing the right shift, you should be very careful. If you're doing the right shift, all right, okay, let's do right shift with 1. If you're doing the right shift, all right, of course, we are shifting to the right. So we'll take this one out because we're only shifting by 1 bit. Then we will not fill in, we'll bring down 0, we'll bring down 1, we'll bring down this 0. But now we need to fill it. We need to fill in. So you should be careful. Whatever you have here, that is what you're going to be filling in. You're not just going to fill arbitrary zeros. Arbitrary 0, no. So here we have 0, and 0 is positive. So to make these numbers to maintain its sign, we will fill in with zeros. All right, we'll fill in with zeros. But imagine that we are working with negative number. So negative number, let's say we are working with 1, 1, 0, 0. All right. So remember, this is a signed integer. All right. Then this bit, this is the most significant bit. It may show that this is a negative number. All right. Then 100 is 4. So this is minus 4. Why this is plus 4? All right. Okay. So using the signed magnitude, but of course not the 2's complement. This is not minus 4, but let's assume that this is from using the signed integer. we use the most significant bit to represent the sign. So here we are having minus, all right, which is a negative number, and this is actually 4. So now if we are to do shift now, all right, if we are to do shift by 1, all right, this would be, we will cancel this one, all right, so we are going to have 0, 1, 1. Then we need to fill in what we have removed. So because this is negative, all right, it's a signed integer and it's negative, we have to maintain that negative. We are not going to add 0, we'll add 1. So please understand the differences. Please understand the differences. If you're working with unsigned integers, you don't need to bother about the sign because you just fill in with zeros. But when you're working with signed integers, you have to make sure that the sign bit is maintained. So here that we have shifted, this is a positive number, so we could add zeros because it's a positive number. But since this one is a negative number, we are not just going to fill in with zeros, we'll fill in with ones. All right, so we'll just fill in with once. So you can shift by 2, you can shift by 3, you can shift by 1. So make sure that you're filling with the appropriate sign bit. Okay. All right. So for unsigned integers, you fill with zeros when you shift to the right. But for signed integers, the behavior may depend on the language or compiler. Okay. So when you're doing 8, all right, this is a positive number because the most significant bit is 0. Okay. So if you make your shift, you fill in with zeros. Okay. So now let's take a look at logical right shift. This logical right shift is only available in JavaScript and Java. It is not available in other programming languages, okay? It's not available in other programming languages. So only available in some languages like Java and JavaScript, fills with zeros regardless of the sign. This logical shift is different from the bitwise right shift. Remember, I just showed you the right shift here, this right shift, it will always consider the sign bit if it is a signed integer. But this one does not care about the sign. It will fill it with zeros. So example in JavaScript, when you say if you do this -8, all right, remember -8 actually has ones or as the most significant bit, but because of this double, remember you can see the sign is even different because this logical right shift does not care about the sign. It would when you shift it by 2, all right, it will fill it with zeros. It will fill it with zeros. And what does it mean? It means that the value have really changed. So the value will not give you what you are expecting. So be careful. All right. This is the logical right shift. Instead of 2, it is 3. You can find it in JavaScript, but don't worry, when we get to programming languages, we'll see them. Okay. So, but most especially, if you don't really understand, grab these things very well, don't too bother about it. Okay, don't too bother about it. So, what's the difference between logical and arithmetic right shift? The logical right shift has 3 of these, and it's available in some languages. And if it is working with signed integers, it doesn't care about the sign bit. It doesn't, this logical right that has 3 doesn't care about the sign bit. But the arithmetic, and it doesn't, since it doesn't care, it will fill in, it always fills 0 on the left. It works well for unsigned numbers. So if you want to use the logical shift, always use it on unsigned numbers. Don't use it on signed numbers. For the arithmetic right shift, which is just 2, this one fills with 0 with a sign bit. So this one fills with sign bit. If the sign bit is 0, it will fill it with 0. If it is if it is 1, it will fill it with 1. So understand the difference. I want you to rewatch this video. If you don't grab it at 4, make sure you take these classes 2 times. Watch these videos 2 times. So this arithmetic shift that has only 2, this thing preserves the sign. It preserves the sign for signed integers. So, but for the logical one that has 3, do not use them. Do not use it on signed integers. Only use it on unsigned integers because it doesn't respect the signed integers. Okay. All right. So these are the differences. The operator, the left shift, it multiplies by it multiplies by 2 raised to power n, and it doesn't care about sign extension. Left shift does not care about sign extension, and the effect is that it multiplies by 2, all right, 2 raised to power n. But the arithmetic right shift that has only 2 of this arrow divides by 2 raised to power n, and it cares it is concerned about the sign. So it will fill in with 1 if the number is a negative number, and it fill in with 0 if the number is a positive number. The logical right shift, which has 3 of these and pointing towards the right, it still divides by 2 raised to power. It divides by 2 raised to power n, but it doesn't care about the sign extension. Okay, so bits notes, key notes here. Bit shifts are faster than multiplication and division. So let's go and do a trick here. Let's go and do a trick. Let's go to the browser. I hope this guy will just open. Let me show you a trick here. If I want to do, let's say, okay, so let me write a new code here. This is JavaScript. So I'll have a variable. I have a variable constant x is equal to, let's say it's equal to, let me say 16, okay? And I want to divide this 16 by 2. Normally, we'll do constant result is equal to x divided by 2, all right? So this will give me, the result will give us, let me console the result, console.log. Don't worry, if you don't understand what I'm doing here, don't worry. Just understand what I'm trying to explain. Since if you have not coded before, it's okay. You will code one day, okay? So now what I'm doing here is that I'm telling the computer to do 16 divided by 2 for me. And if I run this, I'm going to get 8, okay? I'm going to get 8, all right? But there's something we call performance. There's something we call performance when we are writing a program. Now, according to what our slide said that the bit shifts are faster than this division and multiplication. So instead of me to do this, instead of me to do s divided by 2, remember, I will do right shift. Remember, right shift I will do right shift by 2. Remember, right shift is equivalent to the number divided by 2 raised to power the number of bits. So here I'm doing 2 raised to power 2, which is 4. Okay, sorry. Instead of doing 2, I'm doing 1. All right, sorry. I want to do division by 2, so I'm going to use 1, because this will be 16 divided by 2 raised to power 1, which is 2 raised to power 1 will give me 2. So instead of me to do 16 divided by 2, I will do 16 right shift 1. And if I run this now, I'm still going to get 8. The same value. So now, but this will be faster in my program. Remember, since I'm dealing with unsigned integer, I can go with the logical right shift, and I'll still get the same thing. Remember, I'm using this logical right because I'm working with unsigned integer. If I'm working with signed integer, I will not use this logical right. So now this is the equivalent of division. This logical right shift, or the arithmetic right shift, is the equivalent of division. Now, if I want to do multiplication, so I will say x and left shift 1, then this will give me 32, right? This will give me 32. So this is the trick here, okay? But if you don't understand it, no problem. Make a post in anything that you don't understand, make a post in the WhatsApp group, okay? So use logical shifts with unsigned data. You just saw me using the logical right shift on positive 16. Be careful with sign extension when using the right shift operator, okay? So use cases, fast multiplication or division by powers of 2. I have shown you that. Bit mask manipulation. In the next session, we'll teach you about bit mask manipulation, and then performance critical code. Now, if I am to be writing code for embedded systems, I will not be using division or multiplication. I'll be using shift, left shift or right shift, because this embedded system, they need your program to be very, very fast. Don't bother if you don't understand what I'm saying. As you grow in your career, you will understand. For graphics programming, bitwise shift operations are used. Cryptography, they are also used. Okay. So important notes: shifting beyond bits, bit width. If you shift beyond the width of the bit, the result will be undefined, especially in C and C++. All right. Imagine that we have 8-bit integer and you're shifting by 38 bits. You have to shift by less than. You have to shift by less than the number of bits you have. This is very simple to understand. Okay. This here, you cannot say S left shift 32 in a 32-bit integer. All right. You cannot say S left shift 8 in an 8-bit integer. It won't work. Always ensure the shift count is within the bit size. All right. At least the shift count should be we should be at least 1 less than the bit size. Use unsigned types for predictable logical right shift. So whenever you're working with, you want to work with unsigned integer, you want to work with the logical right shifts, make sure you're using the unsigned integers. Okay. So in the next session, we'll be talking about bit masking. All right. I will take time to explain bit masking and bit vector. So thank you very much, everybody. This is where we'll be ending the class. Make sure